All right, hello, Rachel. We're going to do example 1 on section 9.2 notes. We'll do the backside example 2 not tomorrow, Monday. But here's 9.2. It's the same as 9.1, but we are doing mean instead of proportion. So when we were setting up proportion, H0 and H1, here's how this works. For proportion, what was the variables that we used? P. So we would say like P1 equals P2, and then H1 would either be not equal to, less than, or greater than P2, right? That's what we would do for proportion, okay? In this section, we're doing mean, and the variable we use for mean is? Mu. H0 is going to be that mu1 equals mu2, and then our H1 is going to be not equal to, less than, or greater than, whichever one, right? Okay? Or whatever, I don't care. It doesn't matter. Greater than, less than, not equal to. That's how we work for mean, okay? Now, one more thing I'm going to have you write up here is in the formula, they have this going on here. If mu1 equals mu2, what is mu1 minus mu2? 0. So in the formula, when we go to do our calculations, if we are assuming mu1 equals mu2, which we do always, because that's what our null hypothesis is, in the formula, mu1 minus mu2 shows up right here. This will always end up being 0, right? So you don't have to do that part of the formula. Now, x bar is what we use. I don't know if you can see this bar right here. Put him on there if you can't see him. X bar is your sample mean. So that's the data that we are given, right? We're assuming that the populations are the same, but we're using our sample data to do that, okay? So x bar, S1, sigma, all that good stuff, that is all right there, okay? The formula for mean is a lot better than the formula for proportion because you don't have like P and Q over N. It's just S squared over N, right? Okay, look at this mess that we have going on right here, though. Like, everybody gets confused. S, and then we have a 2, and we have a 1.
S squared.
That is S1 squared. That's the first standard deviation squared. This is S2 squared, right? So, like, the 2 over 2 and the 1 over, like, that's confusing. That's just saying your first standard deviation squared, your second standard deviation squared, okay? And these are bars. I don't know if you can see that very well, but make him darker on your formula sheet if you need to. That is what we have for formula. Now, when we're doing mean, the same rules apply. If your n is less than 30, you use the t-chart, okay? If your n is bigger than 30, you use the z-chart, etc., right? Like those type of things, okay? Now, here's the deal. When you're using the t-chart, you have to have degrees of freedom. But the problem is you're going to have two different n's. You have an n1 and an n2. So which, like, let's say in my first n, I surveyed 20 people, and in my second n, I surveyed 15 people, right?
14 and 19.
So my degrees of freedom would be 14 and 19. Which one do I use, though? Because I can only use one of them.
Oh.
No.
19. No, assume less. 14.
You always assume less. You always assume less accuracy because you don't want to over assume. So you use the lesser of n1 minus 1 and n2 minus 1, right? Like the degrees of freedom is the n's minus 1. So you use the smaller one. So we're going to use 14 in that case. Does that make sense? Right. That's what it says here. Degrees of freedom is the smaller of the two. Whichever degrees of freedom is the smallest, that's the one you're going to go with. Got it? Okay. Let's go down to this right here. They give us two things for females and males. When we look at females, we have less females that we surveyed than males, right? How many females do we survey? What is like N1?
Oh.
12 females. And N2, how many males do we have? 15, right? So when we are going to do degrees of freedom, how many degrees of freedom do we use? 11. Not 14, 11. Got it? It's the lesser of the two. So I'm going to write that down over there. Now, is it what? Oh. All right. So write that down off to the side. I went ahead and left these from last year when we calculated them. Somebody put them into a Google Sheet or a calculator or whatever. X bar, the average from those is 3.87. Write that down. The average of the second one is 3.99. Standard deviation of the top one is 0.56. Standard deviation of the second one is 0.40. Got it?
No.
All right. That's what we have. I haven't even read the story yet. Okay, so list those down off to the side because we need those, okay? Listed below are student course evaluation scores for courses taught by female professors and male professors. So we're trying to see if people are rating female professors at the same rate that they rate male professors. Like, do they prefer female professors over male professors? Like, we're looking at the rating scale, okay, to see, what the difference is. Your fish value is 5%, 0.05. To test the claims that the two samples are from populations with the same mean. Okay? Does there appear to be a difference in the evaluation? So, we're going to say that mu1 equals mu2. Okay?
That's your claim.
That's what we're claiming. We're claiming that they're equal to each other. So, what's the second one? Greater than, less than, not equal to. Not equal to, right? Not equal to mu2. We're saying that the average score for females is the same as the average score for males, etc., right? I'm going to also put in here, this might be helpful since we have two mu's going on. Which one is mu1?
Girls.
Girls. So I'm going to say females here. And I'm going to say mu2 is male, so we know which one is which, right? Female, male. Now, it's not so much important when you have equal to, but when you have like less than, greater than, it might be easier to like designate which one's less than, greater than, okay? Or which one's there. So we have two tails. Just like normal. Our fish value is 5%. We have to split it in half. 2.5% and 2.5%. Okay? So that means what percent in the middle? 95. Okay, we have to look up on the table what our critical numbers are. Like, where is this cutoff point and where is this cutoff point? So we're going to look at 95% and we're going to look at how many degrees of freedom? 11 degrees of freedom. So go to your T chart. Go to 95% and 11 degrees of freedom. Tell me what those numbers are. 2.201 and negative 2.201. Okay, that's what we have, right? All right, so those are our critical numbers. Again, we're not going to do the p-value method here. We're going to do just critical value method, and I'll tell you which ones to do on your homework assignment that way, okay? Now, the average score for females was 3.87. The average score for males was 3.99. They are scoring males higher, according to our sample, than they are scoring females. But is the female score lower than the male score enough to say that they're not, like, that they're giving preference to male teachers? I don't know. That's what we have to decide, right? Do you think 3.87 is close enough to 3.99? I don't know. That's what we have to decide, right? So here we go. We have to do our test value, and that's where the formula comes into play. That's this guy right here. So T is equal to, I'm going to put him right here at the bottom. X, do you want me to write the formula out? X1 bar minus X2 bar over the square root of S1 squared over N1. Is it plus?
Yeah.
Plus S2 squared over N2. Okay. All right, now let's plug our numbers in. What is X1 bar?
3.87 minus 3.99.
Yep, 3.87 minus
Over
3.99.
the
Okay, now,
square
hold on.
root.
Judging by that, are we going to be looking at the left tail or the right tail? Left, because 3.87 is lesser than, so we're going to have a negative number, right? So we're going to be looking over here to see where it fits, right? Over.
The square root of 0.56 squared over 12 plus 0.4 squared over 15 equals.
Whatever it equals. Okay, if you need to do it in pieces, do it in pieces. This one's a lot less cumbersome, though, than the proportion one, because you don't have two things to multiply.
Are you ready for the answer?
Sure.
Negative 0.578.
Okay. Negative 0.578. That's what Marcus gets. Anybody else got that? You did not get that.
So it does not equal.
Oh wait, I didn't put it over 12 and 15. I put it over 11.
Ah, gotcha.
No, it does. I got negative 0.625.
Equals negative 0.625.
Yeah, I have a problem.
Is that better? Sarah got that also?
Yeah.
Yes, perfect. Negative 0.625. We would have got the same result, but anyway. So our T value, our test value. This is our test value.
Why are you
Or
crossing
test
out the
statistic.
top? It's
What?
equal, Mallory.
What you talking about?
She said cross out the top. You cross out the bottom.
Okay. So negative 0.625 is going to be right about there, which means he is equal to. Even though the female score on average is lower than the male score, that might just be for our sample. That is not true across the board. It is not low enough to say that there is a difference between females and males, right? They are saying females and males are the same. So that's the critical value method, what we just did up here. I just put it in the wrong spot. But does there appear to be a difference in evaluation scores?
No.
So, quick correct.
No difference in male versus female evals. They are treated pretty well equally, even though in our sample the males were treated higher for average. This was a what? Failed to reject. H not. Claim true. There you go. Okay, happy with that? Same process we've been doing already, but your formula looks like this. Okay, here's the ones I want you to do for homework. Ready?
Yeah.
Go to the homework. Go to the homework. Number 1, you can skip number 1. You can skip number 1. You can skip number 1.
Skip one totally.
Skip 1 completely. We're not going to do number 1 completely. Oh, wait.
You're joking.
Nope, we're skipping number 1. Skipping number 1. Okay? Number 2, you're going to do critical value, and number 3, you're going to do critical value. Okay? We are going to skip example number 4 because it gets split at the bottom of the page and the top of the page, and it's just too confusing to flip back and forth. So if you want to write out like number 4, we're going to skip it, and then we're going to do the confidence interval method for 5 and 6. So those each will be confidence interval method. So, but we won't do those. We won't do those until Monday, right? We'll skip 4 completely and skip 1 completely. So you really have 4. You really have 2 homework problems. That's it. Critical value method. Now here we go. I'm gonna talk about number 2 real quick because I wrote over here this little note.
Z-chart.
Z-chart. How's come Z-chart?
It's over 30.
Both of my n's are greater than 30. What happens if one of your n is less than 30 and one is greater than 30?
Well, you're allowed to.
You have to use t because you can never assume more accuracy than what you have. So you would have to go down to t, right? So there's that. Okay, so we get to use the z-chart to find. So we don't need to worry about degrees of freedom. We don't need to worry about any of that because we're on the z-chart.
What's the degrees of freedom for? For the fish value?
What?
For the fish value?
For
it's
degrees of freedom will tell you. Degrees of freedom will tell you on your chart where these numbers are.
N minus 1, and then it tells you on the t chart.
That's what I asked. I just asked it wrong.
Yeah. Okay. It'll give you those numbers. Okay. It says on here, construct a confidence interval to test the hypothesis for part B.
No.
You're just doing critical value method. Same thing here. Construct a confidence interval. So the part B doesn't really apply. We're going to do those on number 5 and number 6. Okay. So I wrote down T chart for number 3 though, because here's a prime example. One of my n's is less than 30. One is greater than 30. But we said we have to use T in that case, right? Okay, so get moving on those 2. You can get those done. They are not terribly difficult. 2 and 3, just those for homework. Go.
Can I take my test?
Yeah.
Okay?
Help me think of something.
All right, goodbye, Rachel.